So now, so far we've been talking about the transfer functions, right? I mean, and we derived the forward transfer function, the asymptotic transfer function formula. Now, one of the interesting things is, and one of the interesting questions that always arises is the input and output impedances. So the question is, what do we do about the impedances? How do we determine those? Now, what we're going to do, we're going to have a general derivation of Blackman's impedance formula. And you will see it's very effective, very useful in determining not only the impedance, but also helps you understand what kind of feedback you have. So we are going to be focusing on Blackman formula. And in doing so, we go back to our original model. You remember when we thought about this circuit, we said you can have in general a UI input, a UO output. And what we had is that somewhere inside this thing you have a voltage UA, or signal UA, it could be voltage or current, and a dependent source, let's say in this case, which is K, well, it's a GUA. And then we said to determine the transfer function, to determine the return ratio, one of the things that we did, we could say this could be, this is some UZ, and then this became UX, which is an independent current source, and UY, which was the return current. And in the most general case, we scaled this by K. We said, K, return ratio, of course, is determined when K is 1 and UI is 0. That's how we determine the return ratio. So when we did that, we said, okay, well, in this model, we really have two independent variables, UI and UX, two independent sources. And there are two functions of those, UO and UA. So we wrote them in this format. UA is A UI plus B UA and UA, I'm sorry, UI and UX. And then UA is CUI plus DUX. So this was what we did. And then to determine the transfer function, the formula that we have, we said, okay, for K equals 1, well, K equals 1, and when we are determining the return ratio, UI has to be 0. I'm sorry, not the return ratio, never mind. K equals 1, and UZ is 0. So this is the regular behavior of the circuit, right? Under normal circumstances, you don't have the source, right? This was something extra we added, and K is 1. So UZ is 0, which means that UX is equal to UY. But I know something about UY, but UY is in general KGUA, right? So I can plug this back into these equations. So I get UO is AUI plus KGBUA, and then you get UA is CUI plus KGDUA. So we can solve for UA in terms of UI from this one and plug it into that guy. And then we get U over UI. This is what we did before. I'm just quickly redoing it because I'm going to redo some of the results. So from here, you get basically UI, UA is CUI divided by 1 minus KGD times UI, and then I plug this into this guy. So what I get is K plus, A plus KGBC divided by 1 minus KGD, all of them times UI. Therefore, we decided that the transfer function, which was by definition UO over UI, is going to be A minus KGBC over 1 minus KGD. Or we can keep this plus. Now, so we did two things. We said, first of all, we determined this for K equals 1, so this becomes A plus GBC over 1 minus GD. So this is the transfer function in general. But we said that UI and UO could be voltages, currents, or different things, different ports. One of the things they could be is that UI and UO could be the voltages and currents of the same port. So one could be the voltage and the other one could be the current of the same port. If I'm interested in an impedance determination, then the input has to be an I, a current, and the output has to be a voltage. So the ratio of a voltage to a current gives me an impedance. So if I say my UI is the port current, and UO is the voltage of the same point of interest, same port, then what happens is that I can define Z as, which is defined as VT over IT, to be this transfer function. So this is Z in general is that. A plus GBC over 1 minus GD. So that's my Z. But now I can do a couple of other things too. I can say, okay, so that's my Z in general, fine. So I'm doing the derivation of the Blackman's formula, essentially. And again, it's a derivation that you don't need to remember, but you need to know the result. So now the interesting thing is that, okay, but I can evaluate this transfer function when K is 0. Right? If K is 0, what do I get? What is the transfer? What would the value of this thing be? So H for K equals 0 is simply A. Now, in this example, when I choose these variables, that would be what I call the Z0, which is the transfer function when K goes to 0. Namely, I've chosen a reference source, reference dependent source, and I've basically set it to 0. Set the coefficient. I've disabled it. And I'll show you how it works in a minute. So that's A. Now I can determine the return ratio under two circumstances. Two sets of conditions. One is the return ratio when one of these variables is 0. Let's say I determine the return ratio when I of t is 0. What does that mean? If the current of a port is 0, what does it mean? It's open circuit. So I say when I of t is 0, t open is defined as Vt, returned as Uy over Ux when I of t is 0. And I of t is simply U of I. If U of I is 0, Ui is 0, what do I get here? So let's see. What do I get? In this, if Ui is 0, I get my Ua. In this case, Ua is going to be simply Vux. Right? And what is Ui in terms of Ua? It's just GUA, right? It's a dependent function. If I know UA, I know my UI. It's simply GUA. Right? So G times this guy is going to be UY. So this ratio is simply minus GD. So T open is minus GD. How about, so this is one condition. The other condition is that I set VT to 0. If I set VT to 0, then what happens is that, what have I done to that port? If I set the voltage of the port to 0. I've shorted it. So this is a new return ratio when the port of interest, where I'm trying to determine the impedance, is shorter. So again, by definition, this is again Uy over Ux when Vt is 0. And what is that quantity? Vt is what? UO. So I'm saying that this is 0. So in that case, basically I get Ux, Vux plus AUI is 0. Right? And I can solve for what? I can solve for, in this this case? What can I solve for? UI and plug it into here. So I can solve UI is simply minus b over a ux. I plug it into here, I get UA is minus BC over A plus D times UX. But now, I know UI is related to UX through it. If I know UA, I know UI. So I can say this is G times that is simply UI. Therefore, minus UI over UX becomes what? Becomes BC over A minus D times G. In other words, this quantity. So this is basically G BC over A minus D. Yeah. All right. So I've determined three things. I've determined the return ratio under open condition, under short conditions, and I've determined my impedance. So now let's rewrite these in a different way. So I'm going to say, so I determine my impedance to be from the top A plus GBC minus 1 minus GD. And I factor A out of this thing. So what do I have my left with? It's 1 plus that divided by A, so it becomes 1 minus GD. 1 plus GBC over A divided by minus 1 GD. And I would just, and I know what A is. What is A? Z naught. So Z naught times, and I just take this, put it here, multiply it up, minus G. So I get minus GD, or I can write it this way, plus G times D minus BC over A divided by 1 minus GD. Okay. But, oh no, actually, it's still BC over A minus D. Okay? But now, these two terms we have already determined. So, what is the top term? This is 1 plus T short, and this is 1 plus T open. So now, this is easy. So this is the Blackman equation. So this is what we need to remember, not the derivation. So what does this mean? It means that the impedance of any point in the circuit is the, you can determine it by calculating the impedance when you set the reference dependent source to 0, null, basically by setting the K to 0, remove it, eliminate it, null it, times the ratio of 1 plus the return ratio when that port is shorted, divided by when that port is open, the return ratio. You calculate two return ratios, one when that point is shorted, one when that short point is open, and then multiply by what you see without the feedback. And that gives you the impedance. So, alright, so much for discussion. Let me.
This is independent of the choice of the dependent source, right?
This is again independent of the choice of the source. It's valid for all sources, but again, for it to have physical meaning, you want to pick sources that are relevant to the feedback system. If I choose some irrelevant source, what happens is that Z naught becomes Z. Right? So then it doesn't help you in solving any problems. It just basically is as difficult as it used to be. So you want to pick a source that makes the calculation of that impedance as simple as possible. That's Z naught. Basically eliminates the effect of feedback, ideally. If you do that, then this becomes a basic calculation, and then there are two return ratios that you calculate. And I'll show you examples. But now before I say something. This is the best measure. This is the best thing to determine what kind of feedback we have. You remember we had this discussion of whether it's shunt or series or how do you know? Okay, so there's a formal definition. You can define it formally. If T open is smaller, or let's say T short, is smaller than T open, what it does is means that the impedance is lowered, right? And this is a shunt. This would be considered a shunt, if you really want to name it.
This is again contingent on choosing Z naught in a.
For that node, for that point.
Oh yeah.
Right. I mean, a circuit can be shunt or series depending on where you take the output from, right? I mean, I can show you examples of that. And if T short is greater than T open, you see, that's another assumption. See, that's actually a good question you asked. Because a lot of times the confusions arise from the assumption that a circuit is either shunt or series, a network. It's an irrelevant question until you tell me exactly where the input and outputs are. And I'll show you examples, I mean, we'll show you examples that from one node it's shunt, from the other node is series. If you take this node as the output, becomes shunt. This other node becomes series. So you can't define it. I mean, it's the same thing as the question of what are the zeros of a circuit. I don't know. Where is your input and where is your output? So this is what we call in general, but there's something that I actually would like to think about it. Say let's say if T short is 0, then that's what I call a pure shunt. Pure. Well, it means that it's because you can have circuits that are combination. You can have situations in general where these two are non-zero both, and as a function of frequency, they kind of go up and down. So you can have some frequencies where this is higher than that. You can have some other frequencies where this one is higher than that. So for those frequency ranges, this can be shunt, and then after that becomes series, even the same point. So what I mean pure shunt is that basically there's no dispute. Right? And I'll show you what pure shunt is. Again, when we see the circuit, we'll see. I mean, this is what I just named them, but make a distinction. And T open, if T open is 0, I call it a pure series. Okay. Now, so this is called the Blackman equation. It's very useful, but let's see how it's used. And at the end of the day, it's not abstract until you see how it's applied. Right? Does anyone have a good mnemonic device to remember which one is in the numerator, which one is in the denominator? Actually, I think yeah. I don't know. It's just short. The way I think about it, since this is about impedance, is short is lower impedance than open, so it comes first. But again, it's not a very good way. I just like some way to help you remember it. The mnemonic. Yes. But if you have a better one, I'll take it.
When you're
Yes.
wearing shorts, your legs down. When you're wearing shorts, your legs are out and open.
I'll take that. Okay. Do you have a question?
No.
Alright. So let's see examples. Let's do examples. Okay. So I'm going to start with simple examples, and then we get them more and more sophisticated. So the first one, let's do an op-amp in inverting configuration. R1, R2. But this time, let's assume that you have an input resistance. Your op-amp has some input resistance, Ri. And then you have an dependent source here, a voltage source. It's A, Vi. This is Vi. Well, this is with this polarity. Right. So, and this is your input. So let's say I'm interested in the impedance seen from this input. Let's call this resistance in this case, Ra. And this is Vi. So I'll go in that. How do I calculate this? Well, there are different ways. Let me just play a trick first. So I can be smart about it and say, look, I know whatever that resistance is, it's going to be this R1 plus whatever resistance you see looking into here. Rn prime. And make my life easier. So I know Rn is R1 plus Rn prime. That's fair, right? Just sitting there, so it's whatever in addition to that. So I can look into this. So let's first look into that, and then we'll come back to the general one, just to verify. So if I look at this, essentially I'm saying that this is my port of interest, and I'm interested in determining the impedance of this in general. So first thing I have to determine is Rn 0. Well, this is a prime one. So when my source, my independent source, the k is 0, which I have one dependent source here anyway, so it's relatively easy to decide what I will do with this. So I make it k here and set k to 0, and then the source disappears. Namely, this is a voltage source. What does it do when it disappears? It becomes a short. Right? Be careful about this one, right? This is short. So basically, in this case, this is shorted. So I need to determine this impedance. What is the impedance I see looking into that node? Ri parallel R2, right? You see Ri to ground and R2 to ground. Ri parallel R2. Fine, done. Now, how about, so now I have to determine two return ratios, right? So this is a voltage one, so the way it works is that I put a VZ here. So this is Vx, this is Vy. You remember when we wanted to do it in voltage sources, we put them in series. You had seen a lot of current ones, but not a lot of voltage ones. So this is a voltage source. So this is Vx. So I'm interested in, if this is Vx, what is Vy? So if this is Vx, what is the voltage here? This is the voltage divider, right? So I'm determining, right now I'm determining what? T open. So let's do T open. T open, this node this port is open. So if I'm doing open, so it's Vx, this is a voltage divider between Ri and R2, so I get Ri over Ri plus R2 times AV. With a minus sign because of the polarity of this thing, but there's a minus sign in the definition of the T, so they cancel each other, so that's my T open. How about my T, what is my T short? If I short this to ground, what is the return ratio? How much, what is Vy in terms of Vx? 0, right? Because this comes here, but it's short, so nothing makes it here. So T short is 0. So I'm done. Basically, my Rn prime is Rn, well, whatever that, divided by Ri parallel R2 times 1 plus T short, T open, which is basically Ri parallel R2 divided by 1 plus Ri over Ri plus R2 AV. And if AV is very large, what does it do to the impedance? Makes it 0. Goes to 0. The impedance becomes smaller and smaller. The larger you have gain. So this is one way of achieving very low impedance at the input, if you want. You make a shunt input. Now, because of the way we've done it, this is a pure shunt, right? Because this is T short is 0. So this is a pure shunt. Pure shunt means another way of saying, it's another way of saying that you are exactly at the summing node, where the two currents are subtracted. Or pure series means that you're exactly at the difference in calculation points of two voltages. So you can simplify this a little bit more if you want. It's like you can write it as Ri R2 over Ri plus R2. This is not really that informative. We'll actually write it this way. Anyway, you write it, it's just basically. This is even better, in my opinion. The better way of writing it, because it just basically shows you what depends on what, as opposed to a bunch of terms. But, so it tells you that you can lower the impedance. You're lowering the impedance in this case. It's the shunt at the input. Now, if I put R1 in there and recalculate this, and it's in your handout, you can calculate the R indirectly. But now, if you do R indirectly, what you see is that, let me ask you this question. Instead of calculating them directly, just let's do this. So this is a T, these are T open prime and T short prime. Okay? So, but now T open, when this, we are doing it from here. How would it be different? Just tell me what are they? Is T open any different? No? Because you know, if this is open, there's no current. This guy is hanging in the air, right? One end of the resistor is like there. There's no current flow, so it's the same. So T open is equal to T open prime that we had before. Now, how about T short? Now, if you short it here, you still get some return, right? Your return ratio is non-zero. Because now this voltage can be non-zero. But this is not directly shorted to ground. So this is going to be a parallel combination of R1 and Ri, and the voltage divided with R2. So it's going to be some R1 parallel Ri divided by R1 parallel Ri plus R2 times AB, something like that. Now, what you see here is that this is now, from this point, this is not a pure shunt. Still it's shunt, but it's not pure shunt. Because what you have really, your impedance, has a term that increases it, and a term that decreases it. Right? But the term that decreases it is still stronger in general. See, this is again another problem with a lot of this, the other approach to feedback. You always get 1 plus T or 1 over 1 plus T. You don't get both of them sometimes. But this is like a very simple example where you have both. There's something that increases and something that decreases.
So now it's instead of a pure shunt, there's some series.
There's some series component, if you will.
And
If you
can you
think
see
about
it?
Well, this is the series, right? I mean, this is another element of series. Still, from this point's perspective, it's shunt. So we still refer to it as shunt, right? But what I'm saying is that it's really ideal, perfect, clear shunt from this point. If I have other stuff attached to it, it's shunt plus some other things. It's still called a shunt. But sometimes when there's too much of this kind of stuff, there's something like called the bridge feedback, or bridge configuration, which is neither shunt nor series. It's just like, which one is it? So, and at the end of the day, whether or not it's shunt or series doesn't matter. What matters is that whether or not it increases the impedance or decreases the impedance. Whatever you want to call it. And that's why I'm not so keen on the names of these things.
So, sorry.
Good.
Is it possible that in a specific circuit, well, you can calculate T short and T open, and using these two values, you can see that the feedback is shunt or series, right? But is it possible that if you made same circuit with same topology, if you change just the values of some elements, the type of the feedback changes from
Yes.
shunt to series?
Well, yeah. You can show basically how a situation. I'm going to show you an example, maybe today, maybe next time, that we have double feedback. You can have basically a situation where you have both shunt and series feedback. Right? You can have two paths of feedback, multiple paths of feedback.
No, just one circuit is one
Well,
feedback.
see, but that's again something that when you say one path, sometimes you draw one of the paths, but there are some parasitic paths through the capacitors and all those things that can change it. That's how it changes. You can have a circuit where basically T open and T short behave differently in frequency. So at some frequencies, and if you can have that, then you can definitely have one that will basically we're changing the ratio of the resistors. You can change it. Basically, it's a question of which ones you make stronger. Well, and at the end of the day, I'm just saying this because I want you to be able to connect to the rest of the discussions about other people. In my opinion, it doesn't matter what you call it. I'd rather not call them shunt or series or voltage current. It's a question of does increasing impedance or decreasing. It's like, again, the same kind of conversation that sometimes you hear in circuits. Saying, this is current mode logic. This is voltage mode logic. This is current mode logic. Okay, what is current mode logic? Well, can you have just like currents? No, whenever you have currents, you have voltages. Whenever you have voltages, you have currents. A better way of saying this is that this is a low impedance drive. This is a high impedance drive. So a current mode logic is basically one that you have a high impedance drive, driving low impedance nodes. And a voltage mode drive is basically when you have a low impedance source driving a high impedance voltage. Now, then the question is, is it still current mode drive? I mean, if I increase the impedances, what is low, what is high, where do we go from current to voltage? It's numbers. Anyway. Okay, so let's do 4 examples. So let's go back to some of the other examples that we did before. This was we called it the shunt-shunt. Okay, so let's say I'm interested in the impedance of this node, the input node first. Right? So I'm interested in Z in, or R in this case. So what do I need to determine? So which one was my source? So we chose this source, so we'll keep it consistent. So remember, we had the T model here, this ground at RM1 or RM2. This is IS2, IS2. Right? So this is what it is. So I'm taking this, and I am taking this K, and what do I do? Okay, first of all, if I want to determine R in 0, what is R in 0? How do I determine R in 0? It's when K is 0, with reference to the source. Just what you see. Looking down here, you see the output, basically, if you ignore RO, you see anything, you see RM2. This is RM2. So then I have to determine T short and T open. Right? So what is T? Let's do one at a time. What is T? You said short, do the short first. The short is in the numerator, right? What does it mean? It means that I short this node to ground and determine the return ratio from here. So if this is I put something here. This is IX, this is IY. Whatever IX goes there and this does something, it comes back and it's just killed here, right? It's shorted to ground. T short is 0. I don't need to even calculate anything. What is T open? When this port is open, this is the regular return ratio that we calculated before. So if you've done that, we can reuse the result. If you haven't, you just can remember it and you can redo it again. So this is IX, current divided between R3 and R2 and R1. So basically I have R3 divided by R1 plus R2 plus R3. Then this voltage goes by the factor of GM1 here.
Times R1, right?
Times R1, yes, correct. GM1, R1. This is the current ratio. This times this resistor gives me the voltage here, times GM gives me the current again. You're right. So that was the return ratio that we had calculated before. Just redoing it here. So that's it. So R in is basically R in 0 divided by 1 plus T open. And these are the parameters. So it's lowering the impedance. It's shunt at the input. And it's a pure shunt. And you can see this is the summing node where the subtraction or addition is happening. This is the feedback current, right? This is UI minus. Right? This is UI plus. And this is the difference. This is ui plus minus ui minus 1. So you are at that known field. How about the output impedance? If I were to calculate the output impedance, how do we do that? Or out? Again, same trick, but now you have to remember, these will change. So it's a different set of calculations. So R out 0. When this guy is 0, it's not there. It's R3 parallel R1 plus R2, right? What is T short? If I short the output, if I short this node to ground, what is my return ratio? Basically, I short it here to ground, nothing goes there to come back. Everything goes to ground, so this is 0. T open. What is it? If it's open, it's the same as before. Right? It's the same as this T open. Nothing has changed, so it's again the same thing. Well, let's say, call this prime, so it's the same T open. Before. This is the same as that. And therefore, R out is simply R out 0 divided by 1 plus T open, which was a T. So you see that output is also a pure shunt. So basically it means that you are doing a parallel voltage metering. So you're measuring the voltage here in parallel perfectly.
So, again, not spending so much time on names, but so would this be a shunt-shunt?
It's a shunt-shunt. Meaning that you're measuring the voltage at the output and you're returning the current to the voltage current feedback for shunt-shunt. If you're really interested in names. Alright, let's do maybe one or two more examples. Let me just show you an interesting example. This one is a little more interesting. This is also something we've done before, but now in terms of so this. Let's just look at the output impedance. The input impedance actually are relatively similar to the other ones. The output impedance of this guy. So if I'm interested in the output impedance R out, then I know whatever it's going to be this in parallel with whatever you see looking up, right? R4. So I can forget about R4, not make my life easier, right? Just let's assume that R4 is not there, and whatever I get is going to be parallel with R4. So let's say this is my R out that I'm interested in calculating. Okay. Now in this case, I really need to if I'm interested in R out, I really need to take the RO of this guy into account. Because if I don't, basically all I get is just infinity. I get a current source at the output. So yes, but if I want to get something more accurate, I have to take the RO into account. You see what happens. Alright, so let's do that. So if I do that, basically let me just draw a small signal model here quickly. RO to RM2, IS2, IS2, R2, R1 coming in. There is a, this is the ground. I use a pi model here, GM1B, GS1, R3 ground, something like that. So this is what I'm interested in. I'm interested in determining the output resistance. So first thing is I have to choose a source. I can choose this source to make it
Is there any reason that you choose this one? Or?
this is straight in the feedback path of feed forward path, the forward path, not feed forward path. So we could use the other one. This is just like there's nothing magical about it. I mean, you can use anything. Just makes it easier. Ideally, I want something that completely kills the feedback. because that makes my analysis calculation of R out 0 simple. Right? Because if I don't count the feedback, then R out 0 is going to be as complex as calculating R out, or equally complex. I just want to eliminate the feedback as much as I can. So make it as simple as possible. So, alright, if that's the one, so basically the first thing I need to calculate is R out 0. So that means that when this K is 0, meaning it's not there. Right? So what do I see? So what do I have? If I eliminate this, basically. And this is not there either, right?
2 times 1 plus GM.
So what am I looking at? What kind of stage am I looking at? It's like a common source with source degeneration, right? Because this is not doing anything. This is just there's no current flowing in this direction. So this is not important. R1 is not important. You might as well take it out. So this is what you're looking at. And this is again, we argue that's not going to do anything. This voltage is going to be at AC 0. So it's basically a common source with source degeneration. But we know what its output resistance is. Its output resistance is going to be RO2 1 plus, or even making it simpler. It's going to be GM2 RO2 R2. Approximately. I mean, there's a 1 plus term. It's 1 plus that. Or RO plus that, essentially. But that's pretty much the dominant part. Okay, fine. So this comes from what we had before. Now, we have to calculate two different things. We have to do T open and T short, or T short and T open. So what is T short? Namely, what is the loop transfer, or let's do T open first. T open, when I leave this open, I want to see what is the return ratio of the same source. So basically, I take this source, I put an IY here, so this is IX, this is IY, this is IZ. So I want to see how much comes back. Now think about this. If this is open here, what can you say about this current? What can you say about current through RO2? If this is open, it's IS2, right? Has to be. So this current is IS2. This current is IS2. What can you say about this current? If this current is IS2, this current is IS2, what is this current? 0. What is this current? This current is IS2, this current is IS2. 0. So, will anything come back? No. So, T open is 0. Okay? How about T short? So, how do we calculate T short? T short, basically, we need to short this to ground. When we short this to ground, what do we get? It's as if basically I have shorted this to ground. Make your life easier, right? Or VDD. This becomes like a follower. This is like a source follower, right? It's a common drain, source follower. So I have to calculate the gain from here. So I basically, if this is IX, this is going to be R3 minus R3 IX. I'm dropping the minus sign. This is it. There's no current flowing here. This is a source follower. So basically, I have a resistive divider between R2 and Rm. Which is R2 over R2 plus Rm2. It gives me this voltage times the GM of this guy. That gives me the return ratio. Right? I ignore the effect of RO in this case. I basically assume it's very large. It's much larger than R2. If it weren't R2, RO would be parallel with R2 because this is shorter on this side. So this would come down in parallel with R2. So instead of R2, everywhere I have R2, it becomes R2 parallel RO2. If you want to take this into account. Nothing will change. So you can see that from this perspective, basically, what do I have? So what is my output? Is it series or shunt? So basically, my R out is going to be R out 0 times 1 plus T short. So it's series at the output. You remember? I think it was exactly this example where you asked me, say, how do we know series or short? This is how we do. this is the series combination of the output. Now, what if I were, instead of doing this, I was taking the output from this node, from here. If instead of taking the output from there, I were taking the output from here, what would happen? So let's see what happens. We have some. I'm just curious to see whether it's going to be shunt series. Okay. So I'm only interested in knowing whether our open T open is greater or T short is greater. Which one is greater than the other? Right. So in this case, if I'm here, I don't even need to calculate anything, right? I didn't need to calculate anything anyway. If I just wanted to calculate short series or shunt. But so if this is my output instead, I am interested, whatever my R out prime whatever is, R out prime 0 is some number, right? But then my question is really what's my T short and what is my T open? So what is my T short? If I short this to ground, how much signal will come back? What is the return ratio? Nothing, right? Because it's just killed there. Nothing makes it back. So this is 0. So I already know it's a perfect shunt. Right? And whatever T open is, the T open is basically going to be the same thing as when we had before. And this is, T open is going to be actually like the T short there, because it's shorted up there already. You get it? So my T open here is going to be the same quantity as my T short there. So now, if you take the output from this node, it's going to be so this was a series. This is a shunt. Right? So, what if I show you a circuit like this and ask you, what is the circuit configuration? Right? Or, even if I could be even more tricky, but this tells you something. I could just show you this and say, oh, what kind of feedback do I have? What kind of feedback is this circuit? And if I'm asking that question, it means that I'm not answering. I don't understand this well, or I'm trying to trick you, or both. Okay, all right. Does this make sense? Are we okay with this? There's another example in your handout, which essentially I'm not. Okay, so on this one, by the way, before we go to the next one, we did this numerically too. I just basically took these results and I compared it with the SPICE simulations. This is on 265. Where's the numerical example? So we put some values there. We assume the GM of 20 millisiemens for the two transistors and RO of 1 kilo ohm for M2. And R1 is 900 ohms, R2 is 100 ohm, and R3 of 5 kilo ohm. And then we predicted that this analysis, hand analysis gives you if you do it, predicts an R out of 203 kilo ohms. If you do SPICE, you see a low frequency resistance of 203 kilo ohms. And then we did also, just to make it more interesting, added the CGSs and CGDs for the transistors. And if you look at the SPICE simulations, you will see that, of course, you start at low frequency, constant impedance, that's the impedance. And then how the impedance drops, you have a couple of poles, and then you see a 0, and then a pole, and a 1. And then you can basically see what the behavior looks like. There's another example with frequency dependence that I basically did, and you can look at it, I suggest you look at it. Which basically captures the same essence. You can do it, make it frequency dependent. The idea here is that now your T's and R's can become Z's. And then you can calculate it. And we use the methods of time constant and everything that we have to analyze it. So that's fine. I just want to use the maybe last couple of minutes to show you something interesting, perhaps. So let me show you something. And it's not going to take that long.
some kind of positive feedback?
It could be, yeah. Could be. But that doesn't matter, it's feedback, right? In general, I mean, we never in our equations we said feedback has to be negative or positive. I mean, we could make it negative, but it just doesn't matter, just like negative. So, what can you say about the impedance of this? Or what kind of feedback is this? Well, how do I analyze this? The analysis method that we have based on the turn ratio should directly apply here, no problem. So I'll tell you how it works high level, then we can next time maybe we can have to do the full analysis. But so let's take this one. Let's take the T model of this guy and make that, so this is like IS2, IS1 I guess, and this is IS1 and RM1 here. And let's make this the source of reference. So first calculating the asymptotic transfer function. K and K goes to infinity. K going to infinity here basically means that this needs to go to 0, right? Asymptotically. So these two voltages are the same. So let's call this V1, same as V1, a small signal. But then I know something else. I know a couple of things. So I know this, this current is 0. Right? Because this voltage is 0, so there's no current flowing through here. So this current has to be the same as that current. And this voltage is the same as that. So I know Vin minus V1 divided by R5, this current is equal to V1 minus V out minus VO, which is the voltage drop across this resistor, divided by R4. So I'm saying that the current through this resistor is the same as the current through that resistor. That's what I'm saying here. And I can say something else. I know that this voltage is the divided down version of that voltage. Right? So I know that V1 is VO times R1 over R1 plus R2. Asymptotic. So I can eliminate V1 between these two. I can plug the V1 from this into that. And calculate the ratio of VO over Vn. And calculate my H infinity. If you do that, I think I've done it. Something like this. It's just solving the algebraic equation. So, it's interesting, right, isn't it? So this part is familiar, right? This one was, when R4 was infinity. We analyzed this before, right? This was on our circuit, right? So when R4 was not there, this was the ratio 1 plus R2 over R1. It was a shunt, it was a series combination at the input. Series-Shunt, basically, right? The voltage feedback without R4. Now R4 introduces this additional term that can change this. And you can see if you set R4 to 0 or to infinity, this becomes 1. Because this becomes basically 0, this whole thing becomes 1. Goes back and reduces to the previous result. But now, this goes back to something you mentioned. So you said, isn't R4 producing positive feedback? It is. And that's why you get this minus sign. But it doesn't mean that it's necessarily bad. As long as you make sure that this remains smaller than this quantity, means that the positive feedback is still weaker than the negative feedback. And there are two sets of feedbacks in this circuit. Fine. And you can actually use this to do something interesting. What can you do? Even no frequency. No, forget about get what?
Oscillation.
No, forget about oscillation before we get there. No, even let's say I'm going to use this as an amplifier. Even a low frequency. I can increase my gain, right? I can boost up my gain. This is how people used to increase gain in the old times. Positive feedback was used before negative feedback, actually. Because people thought when gain was scarce, said, why on earth I want to use negative feedback to lower my gain? I'm using feedback to increase my gain. So this way you can actually make this, for instance, you can make this 0.9 two cross-coupled MOSFETs, right? This is positive feedback if you think about it, right? Because if this node goes up, means that this node goes up, this is an inverting state. This node goes down, this node goes down again, another inverting state. This node goes up. So it's positive feedback. And you use positive feedback to compensate some of our loss. So you can ask it. And then I'm going to ask you, you know what question I'm going to ask next, right? Is it shunt or series? Why don't you guys think about it? Tell me next time whether it was shunt or series. It's a trick question, obviously. All right, any questions?